Welcome back. I am Charlene and today we are discussing Newton's second law of motion. We'll figure out why seatbelts are lifesavers in a little while. But before that, let's see why a cricketer lowers his hands while catching a ball. Now we know the time to stop the ball is very little. So, a large force has to be applied to change the momentum of the ball. But as soon as the cricketer lowers his hands, the time to stop the ball increases and hence less force has to be applied. Therefore, his hands do not get injured. Lesser impact, less injury. Moving on, from the Newton's first law of motion, we know that an unbalanced force brings a change in the velocity of the object. Therefore, it is clear that a force also produces a change in momentum. The change in momentum of an object is determined by the magnitude of the force and also by the time during which the force is exerted. Hence, the force necessary to change the momentum of an object depends on the time rate in which momentum is changed. The Newton's second law of motion states that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of the force. Now, let's derive this Newton's second law of motion mathematically. Let's assume an object of mass m is moving along a straight line path with an initial velocity u. By applying a constant force F throughout the time t, the object gets uniformly accelerated to velocity v. The initial momentum of the object will be p1 and the final momentum will be p2. On putting the values of p1 and p2, we get the change in momentum. According to Newton's second law, the applied force is proportional to the rate of change of momentum. Converting the proportionality into equality, we put a constant k and put the change in velocity per unit time as acceleration, where k is a constant of proportionality. The unit of force is chosen in such a way that the value of constant k becomes 1. Hence, we get force as the product of mass and acceleration. The SI unit of mass is kilograms and of acceleration is meters per second square. So the SI unit of force is kilogram meters per second square or Newton, which is denoted by the symbol N. If force acting on a body of mass 1 kg produces an acceleration of 1 meter per second square in it, then that force is 1 Newton. In all this, did you notice that the Newton's first law of motion is actually a special case of the Newton's second law itself? This is because when the applied force is 0, then the acceleration is also 0 and the body remains in its state of rest or state of motion. Notice that the Newton's first law of motion is actually a special case of the Newton's second law itself. Now let's finally figure out why we need to be armed with seat belts every time we zip, zap, zoom in that car of ours. In case of an accident, a speeding car will stop suddenly. Due to this, the large momentum of the car reduces to 0 in a very short time. Now the stretchable seat belts worn by the passengers increase the time taken by the passengers to fall forward. Due to longer time, the rate of change of momentum is reduced and hence less stopping force acts on them. This prevents or at least lessens the chances of injuries. No hard impacts, lesser injuries. Now here's what we have essentially discussed in this episode up till now. Number 1, the momentum of a body is defined as the product of its mass and velocity. Number 2, Newton's second law of motion states that the rate of change of momentum of a body is directly proportional to the force and takes place in the same direction as the force. Number 3, Force is also defined as the product of mass and acceleration. Enough of theorizing and summarizing. Till we solve some problems, we'll never know how good we are with Newton's laws. So let's move on to answering some of your questions. The first question is,
a force produces an acceleration of 0.5 meter per second square in a body of mass 5 kg. If the same force acts on a body of mass 2 kg, then what will be its acceleration?
As per the question, we have to find the acceleration of a body whose mass is 2 kg. For the body of mass 5 kg, acceleration is already given. So we can calculate the force by using the formula F is equal to ma. And this force comes out to be 2.5 Newton. Now for the second body of mass 2 kilograms, the force is same. So again, by using the same formula F is equal to ma, we can calculate acceleration of the second body as 1.25 meters per second square. Our next question was posted on our website topperlearning.com. This question goes, what is Newton's second law of motion and how do we reduce it to the first law? Now there are two parts in this question. In the first part, only write the statement of Newton's second law of motion, that is, the rate of change of momentum of an object is proportional to the net force applied on the object. In the second part, we have to reach Newton's first law from Newton's second law. Let's see how. When force F is equal to 0, V is equal to U for whatever time is taken. This means that the object will continue moving with uniform velocity U throughout the time. If U is 0, then V will also be 0. That is, the object will remain at rest. This is the Newton's first law, which states that a body at rest will remain at rest and a body in motion will remain in uniform motion unless acted upon by an unbalanced force. Now, I have a question for you. This is the speed time graph of a car of 1000 kilogram mass. From the graph, answer the following. 1. In which region is the acting force positive? 2. What is the retarding force? 3. For how long is there no force acting? So take a while to think about the answer while I take a short break. Coming up next are some neat exam tips and fundamental facts that could help you score better. I'll be back in a jiffy. Don't go anywhere.